Okay, let's get started. Good morning once again. I'm Tony DeBora. I'm co-director of the Institute for Assured Autonomy at the Johns Hopkins University. And I would like to welcome you to this session on the way forward, which is really intended to be an idea sharing session so that people can talk about ideas and seek collaborators. So one thing we're really encouraging is for you to make a note if there's something that you find compelling that you think you could contribute to. Please make sure that you know how to connect with the speaker. Otherwise, we can help you with that, of course. Just a few words about the Institute for Assured Autonomy. We're a national center of excellence, ensuring the safe, secure, reliable, and predictable integration of artificial intelligence and autonomous systems into society, covering the full spectrum of research across three pillars: technology, ecosystem, and policy and governance. Our goals are to ensure this technology will be trusted to operate as expected, to respond safely to unexpected inputs, and to withstand corruption by adversaries, and also to integrate seamlessly into society. So about the session today, this is a lightning talk format. So we're enforcing the 5-minute rule. Speakers will hear from me 1 minute prior to the time that they need to finish up. The purpose is to present ideas, stimulate further conversations. I don't think we're going to have a virtual meeting room after all. There's just going to be this main session. And QA is deferred, so please be sure to contact speakers directly via email, or you can put your question in chat and we can address your question at a later date. Slides will be made available following the talks on our website. We've grouped the talks roughly into 5 themes: methodologies for assured autonomy, explainability and autonomy, policy and ethics, assured autonomy systems engineering, and safety and security. And we'll work through the speakers in that order. So our first speaker this morning is Richard Hawkins from the University of York. Richard, all yours.
Okay, thank you. Hopefully you can see my slide and hear me okay?
Here we go. Yes.
Yeah. Okay, so based on the research that we've carried out on the Assuring Autonomy international program here at University of York, we've developed the AMLAS approach, which is guidance on the assurance of machine learning in autonomous systems. And our aim with AMLAS was really to provide something practical that people could pick up and use, and that would tell them the things they need to do to assure their ML models and to create a safety case for those models. And this is really one of the key contributions that we make with AMLAS. So there isn't really anything else out there that establishes in any detail the link between insurance activities that are carried out and the safety case that you create for the ML model. So AMLAS is split into 6 life cycle stages, and you can see those on the diagram here. So it starts from initial scoping of the ML assurance through to deployment of the learned model into the autonomous system it's being used in. And you can also see on the diagram that we have an input to AMLAS from the system safety requirements. So one really important point is that AMLAS is taking a whole system approach to ML assurance. So safety considerations for the ML are only meaningful if they're scoped within a wider system and operational context. So those system safety requirements, they provide that really crucial link between AMLAS and the system safety process. So the first 2 stages of AMLAS, that's where we're looking at ML safety assurance scoping and the safety requirements assurance, they put emphasis on explicitly establishing that link between system level safety analysis and the ML safety requirements. And then those ML safety requirements, they're used to kind of weave safety considerations into the ML stages in subsequent phases of the process. So for each of the stages of AMLAS, what we do is define a set of defined processes that describe activities that should be undertaken, as well as the artifacts that are used by those activities or generated from performing those activities. And we also provide for each stage a set of safety case patterns that show how those artifacts and activities from following AMLAS can be used to then structure a rigorous safety argument. And these ML assurance activities, they have something that runs in parallel to the main ML development activities. So we expect assurance activities that we've defined in AMLAS become an integral part of developing an ML component rather than something that's kind of added on at the end. And the feedback and iteration that we show there is really important as well. So we expect that you might need to go back and revisit some of these stages. For example, verification might identify a need to go back and revisit data management and then learn a new model and so on. And I've talked about the importance that we place on linking process activities to the safety case. So the picture at the bottom there is trying to illustrate this by looking at one of the stages. And we can see that the artifacts produced by the activities, which is shown on the left-hand side, are then used to support the safety case, which we've shown on the right-hand side. And they do that by providing either context or evidence to support the safety claims that we need to make in that safety case. And then at the end of the process, the safety argument patterns for each stage can be integrated together, and that will form an overall safety case for the ML component. And as a case study, we've used AMLAS to develop a safety case for an ML model that's used for detecting wildfires from a satellite image. And as far as we know, that's the first complete example of a detailed safety case from an ML component. So if you just switch quickly to the second slide. So just to say really that AMLAS is available as a PDF document, which you can download from this website. It's a fairly large document and fairly complex, I guess. So we've also created a website providing the same guidance, but in a more interactive and searchable format. And then the third thing on there, we've also created a prototype of a tool that you can use to work through the process to integrate to the artifacts that you create. And you can start to use the tool to automatically create the safety case for you. And now we're just doing work developing AMLAS further, so through further case studies in different domains. And we're also looking at how we can extend AMLAS to look at ML models through life rather than just pre-deployment. So time's up. So if you're interested in knowing more, please get in touch. Thank you.
Thank you very much, Richard. Great. Our next speaker is Erin Lannis from Virginia Tech.
Thank you. I would like to make the case that we need approaches that take a data-centric lens to assurance for machine learning. And so when we think about trustworthy AI characteristics, the ones we think about often can be framed in terms of the input space. So we want robustness to small changes in input space that don't change the outcome. We want security against adversarial inputs, such as perturbation attacks or stickers on stop signs. We want to mitigate unintended data bias that prevents generalizability outside of the training data. And we want explainable performance within a well-defined operating environment. So we need to know the kinds of inputs that we need to be able to perform well over. And this should be quite intuitive because machine learning models are highly data dependent. For example, if you take a fixed architecture and the same hyperparameters, but you give it different training data, you will get different model performance. There have been papers on the success of black box transferability of adversarial samples across models, even those that have different architectures, suggesting that there's something about the data and not the model itself that's causing the weakness. And the approaches for prediction explanations are typically model-centric, and they may not locate the root cause. So the classic example is this classifier that was intended to tell the difference between wolves and huskies. And when you presented it with a picture of snow, it was predicting wolf. So it was actually predicting the presence of snow. And so the explainability to a line highlights the salient parts of the image. It would highlight the background. But this doesn't tell you what's causing the problem. To get to the root cause requires an analysis of data coverage. So finding out that the training data didn't have images of huskies in the snow or wolves in more urban environments. So we really have a case of garbage in and then garbage out. And so what we're arguing is that we need to characterize the input space. that the model learns relationships between combinations of features and labels. When we have gaps in coverage of that input space, we end up with a failure to characterize that relationship. So our work has been to create and utilize metrics to talk about the difference between two different data sets, maybe a training data set and a test data set, or a source domain and a target domain. And so we've used this to find that there's a correlation in accuracy when the test data set is well representative of the training data set. When we're testing the model's ability to perform where it should have learned, we tend to have higher accuracy. And when we have test data sets that are very far from the training data set, we end up with lower accuracy. And we're treating these as test sets that test the model's ability to generalize. And then if we can go to the next slide. I also want to argue that we need a comprehensive data security strategy that spans the entire machine learning lifecycle instead of just focusing on model hardening defenses. So there's many opportunities from data collection, data preparation, through model training, testing, and then deployment for an adversary to interfere with inputs, or even for random events or accidents to happen to inputs. And to do this, we really need to bring together cybersecurity and data science experts to establish common jargon and practices. We've been thinking about this in two different dimensions, both looking at how do we protect data at rest versus how do we protect data in transit or in computation. And we believe that we need to bring together inputs from the cybersecurity practices, things that we already know about, and things that are really specific to these new machine learning challenges as we deploy machine learning. So I've thrown up a few examples here, but from the machine learning side, when we have data at rest, we might have problems with inaccurate models. There's opportunities for data poisoning. We may be thinking about extracting the private training data.
1 minute, Erin.
Thank you. And then from the cybersecurity side, we can inform things about access control, maybe using stored hashes to do integrity checks on data to see if data has been manipulated, maybe using digital signatures for auditing and logging purposes. And then on the other dimension, thinking about in computation, when we have distributed and cloud training, privacy versus utility, and physical attacks against the model. And we can come up with ideas, again, from cybersecurity, thinking about, what's the best use of encryption, possibly homomorphic encryption, how do we best utilize differential privacy, and thinking about how do we validate inputs, especially inputs from the physical environment. How can we tell when we're being attacked if these are real inputs coming to the system? So I believe my time's up, and thank you very much.
Thank you, Erin. Our next speaker is John Barris. Hello, John.
Hi, Tony. Everybody can hear me? So good morning. Thanks for including me in this interesting panel and discussion. So this is joint work with my ex-student, Usman Fias, who is now a postdoctoral fellow at NIST and also at the Institute for Systems Research at the University of Maryland. And we have been working for a number of years on what we call trusted autonomy, which requires self-monitoring, self-adjustment, self-learning, and correction for autonomous systems. We basically believe that you should not discuss autonomy without trusted autonomy. And the reason for trusted autonomy is because we want to emphasize the role of the various notions of trust that play in trusted autonomy. Next slide, please. So if you look at the right-hand side of the slide, you have the common examples where I can do exploration, I can try to find things, and then I can rescue, which requires collaboration between humans and machines. If you go to the top left side, I have two specific examples. One is a collaboration between several UAVs that try to go through a window and pick up something on the other side of the window, maybe cell phone rescue or something else. And the second picture is from a joint work we did with ABB to try to do collaborative UAV monitoring of factories. So one of the things we emphasize here is the integration of mathematics from logic and optimization and calculus. And in particular, we pay a lot of attention to metric interval temporal logic for time specification. So if we go to the bottom on the left, we have formal methods where we characterize missions and functions via timed automata. Then we end up with an optimal control problem where the difficulty is on the last line, where in addition to minimizing something with some differential equation and so on and so forth, you have a logical expression. There's a way to translate that to a mixed integer programming problem. You see on the last slide on the left, but these problems you can solve when they are small, but they are not scalable. So an example of how you can solve it is if you look at the middle line, where it says specification in MITL, I have an example from monitoring an airport where I have to go over some buildings, stay over some buildings for a while, and avoid the blue area, which is basically the area where aircraft land and take off. So these are essentially moving obstacles. And by solving this mixed integer programming problem, for small problems, you can see very complicated trajectories in very condensed space pretty fast. In the bottom now to the right, you see two more complicated examples where you have a larger number of UAVs trying to go across the window. And if you are not careful with the specifications, you may create a queue on the window. So you may have to actually give very discrete suggestions as far as how this can be resolved by perhaps creating better sequences, or basically declare that the time specifications cannot be met for the problem. And on the right, on this big box, you can see similar examples where we do the same kind of problems when we try to do robust path planning. Okay, so you see the variations in the path after they pass the window. And that's actually a very big area because we don't have actually very good methods for robustness in machine learning or AI or on these problems. You see two other examples on the bottom right, where we have a robust path planning in a typically dense environment. And this leads us to essentially event trigger control, because you don't have to activate the controllers all the time, but only when you're coming close to violate the constraints. So let me close by where we're going, since Tony asked for ideas. So we are putting these things into a model-based system engineering environment that I have developed over the years. And we are adding to that now machine learning and AI. And also we are adding universal models for machine learning and AI inspired by biology. The other thing we're doing is we're using some recent mathematics for the duality between risk and performance. And we have managed to put under risk many notions like safety, reliability, and security. And that allows us to use this mathematics for problems of trade-off analysis when one of the criteria may be security, another one can be safety. You can try to understand the trade-off between safety and learning. As you all know, in order to learn, you have to come close to failure, but you don't want to failure. So how do you quantify that? And in particular, we're trying to use composability systematically, because since these tools that we have so far are not scaling, we have to do divide and conquer. So we use the logic division, and we also use something that's called contract-based design to provide this composability in our methods. That's all, and thank you.
Thank you very much, John. Our next speaker is Sanja Dogramadze from the University of Sheffield.
Hello, and thanks for an invitation. My talk is really starting from the applications that I've been working on in robotics. The motivation for this comes from the significant gap in the social and healthcare, as the aging population is now drawing a strain on the society. In one of the recent studies, it was a lot of ambition has been put, especially in the health and social care, for utilization of automation in considering all areas of applications. So my focus in the last 10 years was on robotics for physical assistance. And here on the left, you see the system that has been developed for assistance in physical assistance to elderly. So this is sit to stand and walk and other activities of daily living with a modular approach of this overhead robotic system. It has been built and tested. In another application, which is here on the left, you can see it's one of the applications which at the moment has the least assistive technology, we explored robot-assisted dressing. So in both of these applications, safety, trustworthiness, and verification are all open questions. So we tried, and our efforts went into designing experiments with human participants and extracting the data and analyzing the potential failures that happen in this type of environment. Well, our experiments were designed in such a way to put distractions and disturbances in this activity in order to capture the failures in the system and the failure of interaction, most of all. So here you can see on one of the slides is the analysis just of let's say, a simple movement, a simple activity, and how much it actually requires and where all the possible failures can actually come in. So we started with human-human studies in safe robot-assisted dressing. So we looked at where the failures occur. This was particularly looking at failures that coming from the user and failures that coming from the environment. So these failures particularly come from occlusions, from the algorithms that cannot capture the movements of both of the humans, but also we looked at how humans can be disturbed and how that affects their motion. This is particularly been focused on patients with after stroke who potentially have a different spasticity levels. Although most of the data we actually have drawn from human-human studies. One of the direction, except looking at the models and algorithms to develop safe algorithms, we are also focusing on development of digital twins using the data from these studies in order to study closely how we can design and where the discrepancies in the motion and in the force application particularly appear in these results. We would, of course, would like to consider some of this study with real patients. At the moment, we have data from only from healthy participants. We're looking at interested parties to contribute to control, safety, human-robot interaction, and verification expertise. We are currently working on a large program grant in UK, Trustworthy Autonomous Systems with University of York. The two projects at University of Sheffield are currently committed to the resilient autonomy and verification of autonomous systems. I believe that's all from me. Thank you so much.
Thank you very much, Sandra. Our next speaker is Enrique Majada from Johns Hopkins University.
Thank you, Tony, and thank you for your nice pronunciation of my name. So I'd like to make the case here of the need for new analytical methodologies to assure safety in systems that are actually being controlled with machine learning algorithms. So you all have seen cases of these amazing demonstrations where we see outstanding performance of many robotic systems and self-driving cars and so on. But I would argue that next for each one of the so next please for each one of these cases, then basically you have a counterexample in which something did not work. In fact, many of these demonstrations require quite a bit of trial and error over time. And as you can see, even for self-driving cars, there's still a lot of issues going on in terms of how brief they are in the movement and some corner cases that are still not solved. And even, for instance, the OpenAI that was famous for this type of demonstrations, once after some trials, and they decided to actually disband the robotics team, mostly because of the reason of there was not enough data to train these models. It would take a lot of time to make this reliable. So the fundamental question is really how to provide safety guarantees for AI systems in safety critical applications. And And I would argue that this requires new analytical tools. Next, please. So one of the questions that we are asking in our group is like how we can actually provide some methodologies for model-free assurance of safety-critical dynamical systems. So at its core, what you're trying to do is like try to find like a safe set for which like all these dynamics are invariant that allow you to stay there in a safe and reliable way. Okay. Now, this problem requires like solving or verifying actually like very computationally hard tests, like for example, non-negativity of polynomials. And as its core are based on this invariance set. So the idea we're proposing here is relax this notion of invariance, which is a core tool for control, to something that we call recurrence. So next, please. So we say that our set is recurrent if comes back infinitely often. And this allows us to dismantle one big set into small sets all over again. So the idea is we use this to actually show next that recurrent is in fact like a fundamental property that is sufficient to actually guarantee that you are within the safe region. So if you can check recurrence, then this is equivalent to actually showing that the set that you're looking at happens to be inside the region of attraction or like a safe region. Next, please. So this allows us to basically design algorithms that actually can sample the whole region to find like efficiently in a very distributed and parallel way, like regions of your space where you are safe. In particular, next, if you were to sample from this union of spheres, for example, then you will be able to find, so next, please, a point that actually is not part of, that does not satisfy this recurrence property. Next, and once you identify those points, then you start shrinking your set to finalize and learn the region that you want. So the interesting thing of this approach is that it's actually very modular and actually can be run in GPUs. And next, please. And when it's applied to actually learning these safe regions, we're able to actually outperform like state-of-the-art algorithms like sum of square optimization for learning like regions of attraction by orders of magnitude. So what I'm showing you here is a simple case in which we run our parallel algorithm like over basically 15 minutes, and this allowed us to just like thoroughly characterize the overall most of the region of attraction of this set. So as it's core, like what we're trying to demonstrate here is that basically with new methodologies for the analysis of the system, it allows us to provide new data-driven algorithms that are clearly outperforming like the state of the art today. So I'll finish here. Thanks. Yeah.
Thank you, Enrique. Our next speaker is Catherine Pollack from the Johns Hopkins Applied Physics Lab.
Great, good morning. Thanks so much. So I'm working on a project alongside a colleague at the Applied Physics Lab, Dr. Catherine Schwartz, on building better benchmarks for trustworthy data science. And at a high-level overview, our project seeks to create an automated framework and graphical user interface that can allow users to more systematically perform community detection on a network of interest. Now, you can imagine a myriad of different scenarios in which we may be interested in better understanding the interconnected relationship between entities or a network. Now, there are many different ways that we can analyze a network. And one of the more common methods is community detection. Community detection allows us to partition our network into smaller groups or communities that can then go on to inform later downstream analysis. There are many different algorithms that we can use for community detection and pick for our network. And researchers typically pick methods that are more computationally efficient or perhaps more widely used in their field. But the challenge is that, like any other algorithm, community detection algorithms have their own underlying assumptions and limitations associated with them. So if we pick the wrong community detection algorithm, we may end up with a set of communities that don't emulate the true underlying ground truth communities. And this could have detrimental consequences for the conclusions that we make from those later downstream analyses. And so one of the ways that we can go about rectifying this is using something called tailored benchmark graphs. And these tailored benchmark graphs take the properties of our real-world network of interest and model them on a synthetic type of data set. Now, these tailored benchmark graphs, we can then perform various experiments on and explore in order to identify which community detection algorithms may perform well on our real-world network. And research that has been conducted by researchers at APL have demonstrated that algorithms that perform well on our tailored benchmarks also perform well on our real-world network of interest if our tailored benchmarks are actually well designed to emulate the properties of our real-world network. Now, as you may imagine, this process of creating a network, identifying the properties of that network, generating an appropriate tailored benchmark graph, and then running all of these experiments is very time intensive. And so we're hoping that our automated framework would allow for researchers and practitioners to engage in this more systematic process of selecting the best community detection algorithm for their network in a more streamlined manner. And this streamlined manner can help build confidence then in the later downstream analysis that uses those ground truth communities. Now, for our platform, we're planning on initially testing our framework on 2 different types of data sets. Next slide, please. And both of these data sets are related to public health social media questions that are of interest to the lab. Our first data set is a repository of COVID-19 vaccination tweets. And within that data set, we hope to explore communities that we're calling a movable middle. Or in other words, communities that are exposed to both pro and anti-vaccination rhetoric. And this is important because much of the vaccine hesitancy research up to this point has focused on these kinds of echo chambers. But we believe that focusing on groups that are exposed to multiple types of information may provide us with important insights on individuals who may be more likely to switch their opinion from being against receiving a vaccination to actually being vaccine willing or actually taking that additional step to receive a vaccine. Our second data set of interest looks at monkeypox, and we're particularly interested in exploring within this data set how stigma transfers throughout the network over time and how we can identify key influencers that transfer that information across communities. And this is important because studies have shown that stigma often coexists with misinformation, but stigma may be a bit more straightforward to detect using our classical NLP techniques. Therefore, if we can identify individuals who are more likely to propagate stigma between communities, we may be able to link them also to individuals who propagate misinformation through those communities. So if you have a network of interest that you're interested in exploring, or you're curious to learn more or would like to collaborate, please feel free to reach out to Dr. Schwartz and myself. We would love to hear from you. Thanks so much.
Thank you, Catherine. Our next speaker is Matthew Gambale from Georgia Tech.
Hello, good morning, everyone. My name is Matthew Gambale. I'm an assistant professor in my 5th year at Georgia Tech. And I would like to share with you today new methods that we are developing to enable robots to learn in the wild. Ultimately, my lab seeks to democratize robots, placing them in the hands of everyday average end users in the home, in the manufacturing environment, search and rescue and field operations. We don't want these robots just to learn with robot experts. We want them to be able to adapt in the field, to learn from interaction with end users, through feedback, learning from demonstration techniques, and also learn through reinforcement learning on their own. And one of the problems that I have is whenever my Roomba gets a little bit of a jam in its wheel, perhaps sucks up part of a toy from one of my toddlers, it will just cry and have its own temper tantrum and say that it can't keep going. But why can't my Roomba figure out how to learn how to drive again, perhaps with a little bit of extra friction to its wheel. Or if we have robots that fly, drones that experience some damage, maybe a propeller hits something in the air, I think that these robots should be able to learn their new dynamics and be able to keep going without you having to pay a repair technician in order to fix it. And I think one of the a fun way to motivate this is with the Monty Python and the Holy Grail clip of a knight that continuously sequentially loses different parts of its body, but continues with the will to keep fighting. The human is able to relearn how to operate its body and keep going. So in the top right, rather than throwing robots away, I think robots should be able to learn. And we see this in surgical operations as well. Actually, we can think about instead of a robot or a system learning how to repair itself or keep operating rather than repair, keep operating under a new configuration, perhaps we can think about this as an optimization problem. For example, in deep brain stimulation, what we'll see on the next slide is that when you want to actually stimulate a patient for deep brain stimulation to quell epileptiform activity in the brain, it's actually a very similar problem to learning your new dynamics and controlling your body. Actually, there's an exploration versus exploitation trade-off there, where you want to figure out the optimal waveform to have a person-specific effect, a therapeutic effect for getting rid of epileptic activity. And so one of my students, Mariah Shrum, developed an approach called safe meta learning that we have within chance-constrained optimization, where on the left, you can see a distribution of failure cases. You can also think about this as individual people with different brain structures and different types of epileptiform activity. And we want to meta-learn over a distribution of such cases the efficacy of taking an action. So in an airplane case, maybe I'm going to tip my wings and fly a little bit to the left, or maybe I'm going to climb in elliptiform. For deep brain stimulation, maybe I'm going to try a specific type of frequency, maybe a square wave or a sinusoidal wave. I'm going to try some action, and I'm going to get some information about how the state of my system will be updated at the next time step. And I can use that to then learn a dynamics model here called F in the middle that describes the physics of my world, how my world will evolve as a function of the state that I'm in and the action that I'm taking. And then by intelligently taking action to learn a very good dynamics model, I can then exploit that within chance-constrained optimization to figure out what is the action that will most optimize my utility. For aircraft, maybe that's following a trajectory. And then for deep brain stimulation, that could be figuring out the action that's going to best quell the seizure activity. We wrap this within chance-constrained optimization within an integer program, actually back propagating all the way through the integer program. So the neural network is literally encoded within chance-constrained optimization so that we can make that subject to safety, so that the plane doesn't crash, and also so that we don't induce an unrecoverable seizure within a patient by injecting them with an unhelpful signal. And so we have developed this meta-learning approach to automatically learn how to do this safely and outperform prior work, both in terms of the safety of our actions that we're taking and the trajectory we generate, and also the amount of information that we're able to learn from our sampling to update our dynamics model. The work was published in Robotics and Automation Letters, and I'd be happy to follow up with you at any time.
Thank you, Matthew. Our next speaker is Renee Vidal from the Johns Hopkins University.
Thank you, Tony. So the work we've been presenting is about how do we make AI systems explainable. Next. So over the last years, deep learning has become the de facto standard for artificial intelligence, and AI systems are currently being deployed in many real-world systems. So they are beginning to impact how we humans use them. So as AI systems are deployed in the real world, it becomes increasingly important to make sure that they behave adequately, that they are robust, that they're safe. And part of it, it's really the ability to understand why they make the predictions they make. And so this has motivated a lot of research over the last 5 years on how do we make the predictions of AI systems sort of explainable to a human. And much of the state of the art today, it's really based on, say, trying to understand what features were more relevant for making a particular prediction. In particular, in the case of images, you might be interested in figuring out what regions of the image were relevant for making a classification. And the issue has been that once these methods based on important scores of features, important scores of regions have been developed, is we end up as humans debating, was this region important or not? Why was it important? And this has motivated many researchers in the field to argue that the way in which we've been doing explainable AI thus far is not the right way to go, and that we shouldn't be really trusting any of the existing methods for explainable AI that are being deployed. And much of it is really that explainability is an afterthought. It's being looked at as the system was already trained, and now I'm trying to figure out what it did. Next. So what we're trying to push for here is the idea that we should make AI systems explainable by design. In particular, what we mean by that is that we should put the user at the center. An AI system is developed ultimately, if it is going to be used for a human, and that human needs an explanation, then the explanation needs to be in human understandable language. It's going to be domain dependent, task dependent, and user dependent. If I am a clinician and I'm explaining why I made a decision to another clinician, I'll use certain vocabulary. I'll use certain way of explaining. But if I'm explaining the same thing to the patient, I'll change and adjust. So that's why it is user dependent. Of course, the language I'll use depends on what I'm doing. So how do we capture that notion that explanations should be made in terms of words, patterns, and that should be user and domain dependent? So we propose to capture that by having the user define what we call here a query set. A query set might be something like 1 million questions about the task. And if the user is happy about our ability to answer all such questions, then we'll be able to provide an explanation. So one example that is illustrated here is, suppose that the task was simply to classify birds in images. And I'm not an expert in classifying birds, but experts would usually just go through a number of attributes. It's like, is the shape perching-like? Is the shape all-purpose? Is the belly color yellow? And depending on whether the answers to these questions are yes or no, they'll make a prediction. And in this case, even though there might be 300 or more attributes of a bird, with just 7 such questions, you can predict, or an AI system here, the one we've designed, can predict that it's a green jay with 99% probability. And what this tells you then is that you're able to build a system that classifies birds and images, but not only classifies them, it not only tells you it's a green jay, it tells you it's a green jay because it has shape Persian-like, bill shape purpose, and also some answers are no. So the upper parts are not yellow. And so the explanation for the prediction is exactly this sequence of questions. And I've illustrated here this with bird classification, but you can imagine this, and we've done that as well. This can be for diagnosis, medical diagnosis, where the sequence of questions and answers is what symptoms the patient has, yes or no. And like that, we're building these AI systems for a variety of tasks and trying to apply this information pursuit framework to make AI systems explainable. Thank you.
Thank you, Renee. Our next speaker is Leilani Gilpin from the University of California, Santa Cruz.
Great, thanks, Tony. Can everybody hear me okay?
Yes.
Great. So thanks for having me. I'm really excited to see a bunch of familiar faces. So today I'm going to be making the case that we really need to actually explain explanations so that they're actually useful for the types of tasks we'd like to do for accountability, transparency, and even for auditing. The problem is that post hoc explanations are increasingly being used to ensure trust and model safety in a variety of different applications, including safety critical applications like self-driving cars. And in fact, when we think about the term explanation, it's largely a model-dependent artifact that provides an end user, who could be technical or not, a reason or a justification for the decision of the model being assessed. But the problem is that there is a huge interpretability gap of explainable AI methods. If we look at the output of some of these explanations on the right here, we see things like saliency maps or ways that they sort of perturb the image, that you can see a particular part, and those correspond to the layers or neurons that were really important there. And the problem is that I just can't imagine how this is going to be used for things like evidence in the case of an adversarial proceeding, or even ways that this could be used to make better decisions moving forward. There are also different methods, like at the bottom right, thinking about interpretable or inherently interpretable methods like decision trees or linear classifiers. But I think the big problem here is that the definition of an explanation largely means different things to different people. And more than that, an explanation is really lacking two things, at least in the model-dependent explanations that we're looking at. They don't have any type of domain context, and they don't have an ability to talk about their capabilities. When these explanations are wrong, there is no way to correct them. And this is really a necessity when we're talking about things that are safety critical or mission critical. And this has caused, injuries and even deaths in things like self-driving cars. In the human analog, when someone provides an explanation that's incorrect or inappropriate, or you don't understand what they're saying, the explanation can be corrected, changed, or even retracted in certain cases. And so what our motivation is to basically represent explanations as different layers of information, to basically bridge the interpretability gap and explainability by creating explanations at different levels for different people. Next slide. So what our contribution here is what we call accountability layers, and it's essentially adding additional organized explanatory layers for accountable AI systems. There may be multiple additional layers for understanding or interpretation, for the interaction and annotation, and even for thinking about quantification and confidence of the underlying explanation. And the real focus of this work is to motivate the societal need for explanations that we can trust, and ones that users can actually understand at different levels. So if we sort of walk through this framework, the key idea here is that there are many different explanations at different levels. And in fact, in the sort of initial explanation layer, you may have a description of what is being explained, why it's being explained, and what is understood. So actually having the capability to say, most users understand these explanations, and this is why they do. And then in the case that these explanations are not understood, either because they're wrong or because they're inappropriate, or they don't have any domain specifics, what we'll be doing is basically putting this through a user study where either domain experts or even AI experts in the XAI field are able to annotate those with saying, again, what is being explained and what are the capabilities. Then we will put that through an active learning framework where basically we learn new labels and new explanations as we go. And this is largely motivated by the way that these complex autonomous machines largely work. They work in different layers of reasoning, and further, they have backups of different backups. So the idea here is that if we're going to use explanations in these safety critical tasks, we want to have multiple ways to explain them, and we want to have multiple backups in the case that they make different types of mistakes. And the overall goal is that once we have this system deployed, this is very early work, what we're hoping is that users will be able to ask questions and actually drill down on these explanations and say, oh, what would have happened if we changed this part of the system? And so the idea here is that the end goal is that when users are actually able to choose between these different explanation processes, we'll basically be facilitating the same type of argumentation that we use consensus when we are explaining to other users. And hopefully that will facilitate a better common understanding. So this is very preliminary work. So we're just starting to set up the system. So I'm really excited to hear people's thoughts. And if they would like to collaborate, please don't hesitate to reach out.
Great. Thank you, Leilani. Our next speaker is Zoe Porter from the University of York.
Hi, everyone. Can you hear me?
Yes.
Great. Yeah, so hi, I'm at the Assuring Autonomy International Programme at the University of York, like Richard Hawkins before, and Radu and John, who will be speaking later. So the research that I'm going to present to you it really speaks to a central, a key ethics question in assured autonomy, which is when would the decision to deploy an autonomous system be ethically justified? And the research idea I'm presenting here is an ethical assurance argument pattern. So it's a conceptual framework and also an outline of a methodology for answering that deployment ethics question. The thought is that it could be used as a template, perhaps for developers to reason and communicate about the ethical acceptability of the system, or perhaps at a higher level by regulators thinking about whether particular systems should be deployed in particular contexts or approved for those contexts. So the research is deeply interdisciplinary. My background's in ethics and philosophy, and it brings together that background and ideas from ethics, particularly philosophical ethics, with the assurance case methodology, which is typically used to achieve justifies confidence in the safety properties of critical systems. But this argument pattern extends and adapts the methodology beyond safety, as traditionally construed as the control of physical risks, to a wider range of ethical considerations. So what you can see before you is a modular structure of the argument. So this is the highest level view of the argument. And within each of these modules is a key claim. It's hierarchically decomposing. So the claim at the top is supported cumulatively by the claims in the lower modules. So the top, so if we look at if we imagine opening up the module principles-based ethical assurance argument, the key claim there is that the use of the system will be ethically acceptable if all affected stakeholders whose aim was ethical acceptability couldn't reasonably reject the decision to deploy it in the intended context. So this is really grounded in a contractualist notion of ethics, that if everyone could reach this hypothetical agreement, then it would be ethically justified. I should specify quickly that that's a normative thing about what would be reasonable for people to agree on, rather than a descriptive thing, because people could always disagree for unreasonable reasons. Just scrolling through quickly, that top level claim would be supported by the justice argument. So how do we get to support this top level claim? The thought is that no affected stakeholders could reasonably object if the realized benefits from use of the system and tolerable residual burdens from use of the system were fairly or equitably distributed across all affected stakeholders. So the idea here is that you wouldn't have benefits accruing with one particular group and all the risks accruing with another. The key there is the equitable distribution. So there's two parts to that. One is that the benefits should be realized and the burdens and risks managed to a tolerable level. And the second is that the distribution is fair. Now, there's not a lot of time to talk about the methodology for reasoning about the fairness of the distribution. So I'm going to go and talk about the subcomponents. So talking about the realization of benefits, that would be contained in the beneficence module, moving down. So the purpose here is that the system should actually have some measurable benefit. There should be a good reason for having it in the first place. That might be increased mobility, increased safety, sustainability, a whole raft of reasons. But essentially that, and also the idea is this should be realized benefits, not hypothetical benefits. And the output from the beneficence assurance argument is a matrix. This is a benefits matrix, which goes up to the justice argument as part of the deliberation over the distribution, whether it's equitable or not, of benefit and two kinds of risk. And so the benefits matrix communicates what the benefits are and to which beneficiaries. So moving then on to the non-maleficence argument, this is about doing no harm. And the idea here is that this argument shows that the risks have been controlled, and it gives a matrix showing what tolerable risks of harm remain. And to be clear here, risks of harm may be a lot broader than physical harm. So it might include psychological harm, invasions of privacy, harms consequent upon biased systems, societal harms, economic harms. I mean, there's a wide range of harms. And the idea here is that this also outputs a risk matrix, which gets exported up to the justice argument, which shows what the risks are and for which risk bearers. And then moving along to human autonomy, there's a similar thought here, but this is a kind of burden or risk that's not often considered when thinking about the risks from systems, and that is the impact that the system or use of the system may have on the human autonomy of the people in the operating environment. So as these autonomous systems increase in autonomy and their influence and power grows stronger, that can reduce the control that humans have. So this is really to capture that element that we think is an important element in reasoning about the overall ethical acceptability. And the sorts of constraints on autonomy that would be considered here are things like whether the system would be unduly coercive, and a lot of this is reasoned about. It's a question of judgment, but would it be unduly coercive? Is it manipulative? Would it distort the truth, be an agent of misinformation? Questions like that. Other questions that come under human autonomy are whether the risk bearers can exercise can give any kind of consent, or whether there are trusted proxies who would give that consent for them. And then there's another type of impact on human autonomy, which is whether, and this would depend on the system and the context, but whether the human can physically intervene in the system if necessary, or stop it, or whether there are adequate controls in place for it to stop if it was going awry in some way. And so from the human autonomy assurance argument, there's yet another matrix which is showing what remaining constraints on human autonomy remain and for who. And then those three matrices go up to the justice argument, where they're evaluated, where it's considered, what are the benefits and to whom, and so forth, to see what the distribution is. And there in the justice argument, problematic combinations be eliminated. For example, if one group of stakeholders only bears risk, or bears risk but has no autonomy, those sorts of problematic ones would be taken out, and then there'd be it's also a space to reason over trade-offs between particular values, between particular risks of harm or constraints or autonomy, or trade-offs between benefits and harms. And then that reasoning supports this claim that there's ultimately yields this answer as to whether there's an equitable distribution of risk and benefit. So very quickly, just to add to that, the transparency module at the bottom is supportive.
1 more minute, please.
Is supportive in that it gives the relevant evidence, or explains the reasoning behind the claims that are made in the other modules. And at the top, the 4 principles confidence argument, that's an argument that justifies grounding or structuring this framework in these 4 principles, which originally actually take their inspiration from medical ethics, but are also applicable to this field. So finally, just to wrap up, next stage for the research is we're producing a worked example with this with a partner, a healthcare AI firm, who have a conversational agent that calls people up after cataract surgery, well, lots of different types of surgery, but this particular one is cataract surgery, to determine whether they've got post-operative complications. So that's where we're at now, is trying to produce a worked example of this. And if anyone would like to talk to me about it, I'd be delighted to hear from them. Thank you.
Thank you very much, Zoe. Our next speaker is Professor Radu Călinescu, also from the University of York.
Thank you very much for the introduction, Tony, and good morning or good afternoon, everyone. So my talk will be about a technique we've developed within the Assuring Autonomy International Program, but also in collaboration with the Trustworthy Autonomous Systems Program in the UK and colleagues at NASA Ames. And this is about the work we did for the integration of deep learning perception into autonomous systems in a way that can provide us with guarantees. And the work is very much underpinned by the observation that one of the qualities that helps humans make good decisions is our ability to distinguish between scenarios in which maybe our perception is quite accurate, like you see in the image on the right, road is clear, and scenarios in which perhaps we cannot really trust our perception, which is the example of driving in fog on the left-hand side. So this also applies very much to deep learning models, except that we cannot tell very easily when the model is operating in fog and when the model is not. Next slide, please. So what we are doing actually to figure out, to make this this distinction between the perception of an autonomous systems being trustworthy or otherwise, is to apply a number of verification methods to the neural network to distinguish between situations in which maybe we should be trusting the network's prediction, or maybe on the opposite, we should operate conservatively. And indeed, we do not apply methods that are anything new. We can just take from the research literature methods such as model confidence threshold, local robustness analysis, and so on. But through a mechanism of, wisdom of the crowds, these are still sufficient to give one a level of confidence that in some cases one can operate more freely, trusting the predictions of the perception of an autonomous systems, whereas in others one needs to be particularly conservative. Next part, please. And what we do with this information, once it is obtained through the application of multiple verification methods to the deep learning perception, is to combine it with a state transition model of the system and its environment, and to then apply techniques from the area of parametric model checking and probabilistic model checking to synthesize controllers that satisfy certain requirements with respect to the level of risk that is acceptable, as well as optimizing a number of optimization objectives, such as maybe the time to carry out a journey in an autonomous car, or in the energy that is required for that. And that gives us a number of Pareto optimal controllers. What's particularly pleasing about this kind of solution is the theoretical foundation that, under certain assumptions about the data available for the initial verification, proves one with guarantees that these requirements will be satisfied. And indeed, the more verification methods one throws at the problem, the more likely it is to come closer to the ideal solution. Although we also have a theorem that the ideal solution, where the perception will always be perfect, cannot be attained. So we kind of call that the live perfection to God theorem. We apply this to a number of case studies. Next part, please. Of which one involved monitoring the driver of a level 3 autonomous car, which is meant to drive autonomously within its operational design domain, but to give back control to the driver every so often. And in this case, the autonomous system was tasked with drawing the attention of the driver. If you can start this video, please. To the fact that sometimes they are losing situational awareness. And there are a few tens of seconds, I believe, of this demonstration, which was done in a test bed at the University of Virginia. So as the driver is monitored through a number of sensors, various warnings are issued when the driver doesn't pay attention for a period of time. So I will wrap up here. I place the link to this paper currently on archive on the first slide. So if you want to learn more about the technical details of the work, you'll find them there. And I'll be very happy to receive questions via email, I believe, and to engage in collaboration on this interesting topic. Thank you.
Thank you, Radu. Our next speaker is Brian Reed from the FBI. Brian, I don't think we're able to hear you. At least I'm not.
Hello?
Yes, there we go.
Okay, thanks. Sorry about that. So I'll start with a background of AI at the FBI and then explore our efforts at ensuring proper ethical governance of AI here at the FBI. So the mission statement of the FBI is to protect the American people and uphold the Constitution of the United States. As such, we have a long history of employing technologies that can enhance our capabilities and allow us to better carry out our mission while operating strictly within the bounds of established law and policy. The use of AI at the FBI is certainly no exception. In practice, the AI use cases that we see here typically fall into two broad categories. The first, triaging large amounts of data, be it text, digital audio, or video. And the second is one of biometrics, such as facial recognition. Now, both for the governance of both of these broad categories, the FBI is unique in its role as both a law enforcement agency as well as a member of the intelligence community. For the law enforcement side, we look towards Executive Order 13960, promoting the use of trustworthy artificial intelligence in the federal government. And for our national security systems, we're covered under the Office of the Director of National Intelligence, the ODNI's Principles of AI Ethics for the intelligence community, and the associated framework promulgated with it. These two authorities are similar, but not identical requirements. Now, while the EO and the ODNI framework describes conditions that must be met for AI employment here at the FBI, of course, many other organizations, including, I'm sure, some folks on the line, have come out with similar ethical standards. Now, even though the FBI isn't bound by these external or outside standards, we still need to understand the ideas behind them and be able to meet them in the interest of furthering our partnerships around the world. This ethical interoperability, coined by, I believe, Dr. David Danks, is a research area that helps the FBI in our desire to be able to share tools, knowledge, and results with our external partners. So, with that background of our typical AI use cases as relevant authorities, I'll dive into a little bit about the types of work that we've done and continue to refine around AI governance here. We first identified and grouped a list of standards across various ethical, policy, and guidance reference materials, and then defined technical and procedural controls that we could enforce and, I guess, create within the FBI internally to address each area using our standardized must, should, may language. An example of that might be the AI system must audit who interacts with the AI and the inputs that they provided. The most important controls that we've identified is that all of our AI use cases each have direct human accountability. In other words, a human being is ultimately accountable for any actions taken, not the AI system. And of course, this mapping of procedural and technical controls alone is not sufficient to make our systems ethical. We extended practice of an AI Ethics Council, which has been stylized after institutional review boards, IRBs, commonly used when experimenting on human subjects. And so we do this to formalize the rigor that we would expect in ethical evaluations, but it also enables us to be responsive to the rapidly changing environment of artificial intelligence, AI ethics, and research across both of these fields. So in addition to the controls, the Ethics Council, we also have a formal structure for engaging external subject matter experts, which has been absolutely invaluable. Forums like this, such as this, for example. And with that, I'll wrap up. Certainly interested in hearing from anyone who is in, I guess, pursuing this rapidly evolving field. Thank you very much.
Thank you, Brian. Our next speaker is Tyler Cody from Virginia Tech.
Hi, I'm Tyler Cody. I'm a research assistant professor at the Virginia Tech National Security Institute, and I'm pleased to be here today to share results on open and closed systems engineering of learning systems. So machine learning is an emerging technology with few formal engineering frameworks, I'd argue, to guide its application. And today we've heard about some lower level solution methods as well as some high level concepts, but I'd argue still that their theoretical frameworks for understanding the interrelationships between systems and their learning processes are still underdeveloped. It's not clear, certainly not clear from a systems perspective, what the first principles of engineering learning systems are. And while best practices and lessons learned are beginning to pile up, without a basic lattice work of first principles that we can relate them to, it's not clear when, where, or why those are applicable. So my research is targeted at describing learning in formal systems terms so that we can synthesize results from machine learning and learning theory into first principles for systems engineering. And in doing so, construct a lattice work on which we can hang those best practices and lessons learned. So to underscore the scope of discourse here, I want to distinguish between pure AI research, which typically focuses on the optimization problem, the optimization formulation, and related concerns, and AI systems engineering research, which alternatively focuses on engineering processes, which, if followed, result in AI solutions that meet stakeholders' needed outcomes. Now, there's often an intermediate area of research between these two that's focused on so-called pillars of AI and machine learning, like explainability, trust, security, bias, scalability, and so on. But I want to note that while these areas are termed AI engineering research, or to constitute AI engineering research by some, like Carnegie Mellon's recent group that formed, they really concern properties that we'd like our AI solutions to have. And often in research, these properties are considered in isolation. And so while these properties are important, true AI engineering is incomplete without systems engineering processes that realize those properties in engineered learning systems. And correspondingly, then test and evaluation processes that make sure that those desired properties are actually holding. Okay, you can go to the next slide, please. And so this realization led my research towards developing a general model of learning systems and working out from the first principles of general systems theory and abstract systems theory. I defined a learning system in terms of open systems, that is, input-output systems, namely as a cascade connection of learning algorithms which approximate functions and the approximations they produce. Okay, so I treat learning as function approximation. And this is exemplified by the figure on the left. And from this research, from a systems perspective, there's three key takeaways. The first is that learning systems are composable input-output systems treatable with functional requirements. The second is that learning systems have appreciable levels of abstraction, as I illustrate here, and we can use those for specification, analysis, and characterization, and system identification. And thirdly, that structural and behavioral stability, like for systems in general, are fundamental precepts for engineering performance, and thus key precepts for design and operation, as well as regulation and policy. And so those three key high-level takeaways are good, but there's another takeaway, or really a limitation rather, in this concept of open systems. Implicitly or explicitly, most established systems engineering processes take an open systems worldview, a worldview that considers the universe to be filled with input-output systems that are floating around, briefly interacting to create capabilities. This view lacks the nuance necessary to appreciate that the intelligence of a learning system is not exclusively a property of the system, but a property of the relation between the system and environment. In other words, there's significant coupling effects between intelligent systems and their environments. Or simply put, from my view, intelligent systems are systems that dissolve boundaries. Even if intelligence can be relegated to a specific component at conception, over the life cycle of that system, dependencies are going to form between the intelligent component and other components, other subsystems, and the environment it's operating in. And so in this way, intelligence has this dissolving effect on system boundaries, which are typically functional and fixed, but are now crisscrossed with all these information-based dependencies. So in the space of closed systems, there's open questions that include, how do we scope intelligent systems to include these dependencies that are outside their functional boundaries? How do we identify what dependencies are actually core to the intelligent systems achieving needed outcomes? And also to research what failure modes are attributable to such closed system phenomena, or really a lack of appreciation that we have to also engineer the relation to environment and not just the system. So I'm just starting to peel back the curtain here on these ideas, especially on the closed system phenomena. But I'm grateful for the opportunity to share my research with you all today, and I look forward to hearing from anyone interested in these lines of effort. I encourage you to check out the reference papers here and contact me at tcody@vt.edu with any comments or questions. Thank you.
Thank you, Tyler. Our next speaker is Richard Wronski from Charles River Associates. Charles, we're not able to hear you yet.
Sorry about that. Thank you, Tony. Can you hear me now?
Yes, we can.
Great. Welcome to all of you in the audience joining us for today for this talk on building trust and assured autonomy. I'm Rich Wronski from Charles River Analytics, not to be confused with Charles River Associates, although we are both in a lot of similar businesses. So let's start with a common scenario among managers who are contemplating the introduction of autonomous systems into their operations. Imagine, if you will, you arrive at your office one morning to an unusual buzz among the staff and your boss waiting beside your desk. Our drone fleet just became self-aware, she says. What do we do about it? Has this fear ever crossed your mind? How could this happen, you think? What does it even mean? And yes, exactly what do we, or I, do now? Well, at Charles River Analytics, we live and breathe such questions every day as we develop assured autonomy solutions that you can trust, not only upon their initial deployment, but into the future as well. As designers of autonomous systems, we must all understand this harsh reality. Basically, if operators and their stakeholders can't trust in the autonomy that we build, the system will never get the buy-in that it needs to see the light of day. So the integral roles of advanced AI, machine learning, architecture and design, systems integration, test and evaluation, and responsible accreditation are all critical to developing and deploying capabilities in this evolving ecosystem in which learning systems will ultimately become the norm. In considering architecture and design, knowledge of the underlying technology with respect to sensing, perception, and reasoning is absolutely core. On top of this, today's artificial intelligence enables autonomous systems to dynamically learn and improve from new data and experiences without being explicitly programmed to do so, along with minimal to no human contact. This certainly presents some interesting challenges, especially for test and evaluation, and for accreditation as well. More on that in a minute. But familiarity with the underlying technology is not enough. Marrying it with real-world operational knowledge is critical. Having systems integration expertise is yet another critical role in this ecosystem as we seek to bring together many of these base platforms, sometimes hybrid in nature, along with specialized hardware software applications. So I mentioned test and evaluation. This is an area of considerable interest and ongoing challenges for us and others in this domain, as we must adapt traditional approaches to the specific needs of autonomous systems. So what makes autonomous systems unique in this respect? Well, it really boils down to two things. The first is complexity. This is embodied by tons of conflicting behaviors that drive thrashing as these systems try to manage their actions in the face of competing needs and priorities. And this complexity also results in a set of unknown edge cases. Traditionally, these edge cases are relatively easy to define for systems with finite capabilities operating in well-controlled environments. But this is different for autonomous systems, as modeling and simulation has its limitations. We simply can't model the world at full fidelity. So we supplement modeling and sim with real-world experimentation to gain a richer understanding. But edge cases remain a constant battle, going back and forth between the limited modeling and sim environment and real-world testing. We still can't quite capture all of these edge cases. So what do we do about it? How can we imbue autonomous systems with enough ability to reason about these edge cases on their own? Well, one of the things we do is design guardrails for safely aborting when a system's perception of the world ceases to be within its knowledge scope. I will say, however, there's lots of R&D still required in this area, and it's an ongoing area of research for us. The second unique aspect of T&E is dealing with the adaptive nature of these systems as they're designed to continually learn as more real-world experiences are gained through operations. On the plus side, they can learn new edge cases. This is good. But on the negative side, how do we know what they're learning, and how will that newly gained knowledge impact how they'll deal with the guardrails that we've previously designed in? Finally, accreditation is frankly a huge challenge. It's nice to see or hear some of the discussion of this in some of the earlier presentations. I will suggest that to ensure success, investment in policy is every bit as important as R&D, and that comes from an engineer. So I absolutely fully embrace that. So I'll leave you with this. Bringing these skills and knowledge together more often than not is a collaborative effort by partners across the design, test, end user, and accreditation communities. At Charles River Analytics, we're always looking to form teams that can confidently deliver on the assured autonomy dream and avoid that real-life nightmare scenario like the one I described at the outset of today's talk. So thank you all for listening, and I really hope to hear from many of you as we take on these exciting challenges going forward.
Thank you very much, Rich, and we'll be sure to correct your affiliation in any materials that go out afterwards.
Thank you very much, Tony. Appreciate it.
All right, our next speaker is James Stewart from Trojan.ai.
Thanks, everyone. Pleasure to be here. Our team works on risk management and security of AI ML models through a focus on stress testing and auditing. We support research out of the University of British Columbia and Lakehead University in Ontario. We're a small team of 12, and we've been building solutions since 2019 to address two problems that are unique to AI. The first being that the AI pipeline is uniquely vulnerable to attacks because the inputs into the AI pipeline fall outside of traditional cybersecurity perimeters, both during training time, whether you're gathering data or consuming open source data, or you're engaging with third-party annotation services, or even if everything is locked down and you might have an insider threat, or even quality issues with the data. So that data is susceptible to vulnerability. When you typically take a model off the shelf and you do some sort of transfer learning, again, there's supply chain issues with that, and of course the inherent limitations of AI, which I'll talk about in a sec. And then when you deploy your models into the real world, you're most certainly taking inputs from that real world, and again, it's susceptible to distribution changes and potential malicious adversarial attack. The second problem that we consider is that of the long-tailed edge cases, and we've heard a bit about those. And even if you build your model correctly, you take your training, you split up your data into training, testing, validation. The problem is all of that data typically comes from the same distribution. And it's not until you deploy into the real world where you encounter the unpredictable black swan edge cases. And those edge cases, because they're unpredictable, they can't be addressed proactively in the lab ahead of time. And in a long-tail distribution, over up to 50% of occurrences that could present to your model are actually in those edge cases. So that paired with the vulnerability in the pipeline make AI really uniquely vulnerable. So to this end, we've been building a stress testing and audit platform for computer vision, natural language processing, and tabular structured data. Basically allows us to stress test or fuzz test models, synthetically expanding the distribution of testing data, both naturally occurring and adversarially crafted perturbations. But what I really wanted to share today is the culture shift that we are witnessing, hopefully to help practitioners recognize where an organization falls with respect to AI ML risk maturity. Since 2019, when we started early on, most people were like, I don't see a problem. Are these even real? And we've heard about sort of the importance of data science working tightly with cybersecurity folks. I think the problem is data science folks don't necessarily have the malicious DNA to see how innovations can be used against them. And cybersecurity folks don't necessarily have the expertise in deep learning. So there's a bit of a gap. That quickly evolved to, okay, there's a problem, but it's not my problem. That's a data science problem, not a cybersecurity problem. But again, if planes are falling out of the sky, it doesn't really matter whose problem it is. It's everybody's problem. It quickly went from that to, okay, there's a problem and we've got this. We can solve this. We don't need any help from other teams. And just 2 weeks ago, we heard a Deloitte analyst say, there's an active war between data scientists and security folks. And that really hit home because it's aligned with what we're seeing. And I think we're just peaking at that point and starting to come out the other side. We're starting to see organizations with mature governance frameworks, ones that have been working on these governance frameworks for models for over 3 years, and they're actually collaborating across teams with risk management, QA, data science, security, and they're now looking for quantitative tools to actually evaluate the risk at the model level with executive involvement. And more recently, in the last couple of weeks, in fact, we've seen examples of data science teams actually reach out looking for tools to verify their good work, which is sort of that we're coming out of that sort of peak, and we're hopefully starting to see data scientists, and I say this with all love and affection because I like to think of myself as a data scientist as well. There isn't a profession on the planet where your work isn't verified from people outside of your team. One other thing I'd like to leave you with is on the trustworthy and responsible AI. These words are used interchangeably quite often. Trustworthy AI, you can't build trustworthy AI. It has to be earned. And I know this is a nuance, but we feel it's very important for sort of setting up conversations. You can only develop and deploy AI responsibly, and then it's really up for the end stakeholders and consumers to deem it trustworthy or not. We're always looking for partners and collaborators. Would be pleased to connect with interesting folks after these sessions, and I appreciate the opportunity to speak.
Thank you very much, James. Our next speaker is John McDermott from the University of York.
Hi there. Good morning. John McDermott here. Really good to be able to speak to you today. Earlier today, you heard from my colleague Richard Hawkins talking about assurance of machine learning. Complexity in autonomous systems really comes from internal mechanisms such as the use of machine learning, but it also arises because it operates in complex environments where we're relying on the autonomy to make decision making that otherwise would be the responsibility of human beings. And if you could flip to the next slide, please. Oh, it's already said that. Next. So what we've been working on in the Assuring Autonomy International Program that I direct is a process for assuring the safety of a complex autonomous system in its operating environment. So the system as a whole, and Richard earlier talked about dealing with machine learning components. What this does is it integrates system safety processes into the overall development process for the autonomous system. And if it's followed, it ends up with a safety case for autonomous systems. Safety cases are more popular this side of the Atlantic than in North America. But actually, if you don't build a safety case, it still gives you a checklist of the sort of information and evidence you would need in order to have confidence in deploying the system. So there's 8 stages here which lead you through the process to build a safety case or to identify relevant information. It starts off by defining and assuring the operating context, because the same system operating in a desert or on a busy urban road has a very different set of environmental hazards to contend with. That flows into identification of hazardous scenarios. One of the natures of these complex systems is you can't do an exhaustive analysis, but what you can try to do is to identify those scenarios that are particularly challenging and therefore going to give rise to hazards that are indicative of other things that you'd have to manage. That's quite standard. I think one of the things that's really important that's perhaps not typically done is to develop what we call a safe operating concept. So this is a set of rules or principles by which the system is going to ensure safety, and we need to demonstrate that that's met. So this might be a set of rules it will follow, how it's going to avoid hazards it might cause itself, but also how it's going to mitigate those things that the environment throws at it, which it can't entirely avoid. I don't see this as being very widely practiced, but I think is actually extremely important. From defining that concept, you can flow forward into a much more traditional safety engineering process, look at the requirements that flow out of that concept. Those then flow down into design, and we can look at hierarchical decomposition of the systems and assurance at each of those stages. So, of course, in an ideal world, you might do safety top down, but in practice, you can't. You need to also work bottom up. And when we make design decisions, we discover new mechanisms that can emerge bottom up. And one really important thing here, again, which I don't see done sufficiently often, is to look at what happens when these systems operate out of their intended context of operation. We all talk about operational design domains. We tend to use the term operational design model to not be tied to autonomous vehicles. But the system can find itself out of that context if it's limited by weather. You suddenly get a rainstorm that means the system is outside its operational context. The designers can't just say, oh, sorry, it's not meant to be here. You have to do something to ensure it's safe. Or so for a maritime vessel, it might be saying, well, it's meant to work up to sea state 4. It's now all of a sudden in sea state 5. What does it do? So that becomes an important part of the overall safety assurance process and safety case. And of course, we have to do verification and validation. Again, our processes look at that, but there are quite a lot of unanswered questions if you try to get into the detail, what the right balance is between virtual or synthetic testing and real world testing, for example. I don't think we're going to actually come up with a hard answer to that. I actually think this is going to turn out to be situation specific. So really what I'd like to leave you with is what a systematic way of approaching these issues of assuring autonomous systems in their complex environment. This process will link down and connect with AMLAS, the machine learning process that Richard talked about earlier today. I don't think it solves all the problems, but I think it gives a framework for addressing those problems in a systematic way for a particular system when you understand the context in which it's working. So thank you very much for that. I'm afraid I can't be with you very long, but you can contact me, email me if you have any follow-up comments or questions. Okay, thank you very much.
Thank you very much, John. Our next speaker is Jim Liu from SOCAT and Johns Hopkins Carey Business School.
Thanks, Tony. I'd like to thank Veronica, who's doing a great job keeping time. My name is Jim Liu. I'm an associate professor at Johns Hopkins in the business school, teacher of the Cryptos and Blockchains course, which I proposed in 2017 and 18. That was received in a particular way ever since I've been teaching that course. And, our MBA students are very excited about this new technology. Some of this stuff is sort of joint with Tony and the Institute for Assured Autonomy. There was some sort of pings to the IAA about risk in blockchains. And so, we started thinking about, is there a way to see what are the risks in blockchains? And just to recall, blockchains from our perspective is just the development of the internet from Web 1, which was read-only, to Web 2, which was read and write, to Web 3, where we're at now, thanks to Satoshi, where it's read, write, and sort of own or move digital value. So what we decided to do is we scanned around and we noticed that a lot of times people were talking about their own networks and, how can we compare across different networks? So whether it's Bitcoins or Ethereum, Cardano, Polkadot, and so forth, we wanted to sort of see a map. And we were inspired by the Johns Hopkins COVID risk map. And if there's anybody who worked on that project, I'd love to, meet with you guys and just understand how you guys did that. So our idea here, and it's just work in progress, is to present a very transparent way to understand risks. And you'll see in the next slide, and this was actually kicked off at the beginning of the summer, so it's very recent, and it's a collaboration with SOCAT Asset Management, also IAA. We had some interns who were Johns Hopkins undergraduates in the CS, also a graduate student who completed successfully his defense in economics. But basically, we wrote a paper here that's going to be published forthcoming in the Journal of Financial Data Science in 2023. And basically, what we're trying to do is blockchain's risk is very complex, but how do we sort of think about this? And we are the first to say that we don't understand it fully. So we lay it out there so that people can sort of pick holes into it. And, we want to make sure that this is always very transparent. So if other academics want to get involved, that's great. Industry, that would be wonderful. And also for regulators to come to discuss what their views of risk. So one of the things that we're thinking about is there are different stakeholders in each of these blockchains. There's the users, there's the developers, the regulators, and sort of environment and society in whole. So these are the different stakeholders. I'm sure there's many others, but then what we're trying to do is we're trying to understand the risk across different sort of dimensions. So one of the dimensions is obviously the operational component of it. And one of the things that we did was we estimated the transactions per second. Was it per second or per block? We had a few debates about that, but so far we've done it by some, time period that's pulling across. One of the things that's really interesting is we always want to go and join the blockchain network. So we're pulling data fundamentally from that network. As an interim solution, we may, join a third party just so that we understand it. But ultimately, we want to join the Bitcoin network. We want to join the Ethereum network and so forth, and then mine the data from that node. And so it's a really sort of fundamental approach to this. The other thing that we're thinking about also is, from an investment standpoint, from a business investment standpoint, what are the risks? Volatility is only one measure of risk. In the business school, we teach capital asset pricing model and APT, and these are sort of sensitivities to the market factor. So what is the market in cryptocurrencies? Is that a market cap weight of all the cryptocurrencies, or is that Bitcoins? So these are some of the things that we're sort of trying to figure out. And then finally, what about the business risks, right? So many of these networks take developers and they want to grow their community, and they become more and more exciting as the community grows. So, you know, if you are not bringing in the right members across the world in this community, it's difficult to sustain these things. And the switching costs for it as a developer to go from one network to the next network, if you understand the coding language, it's very easy to do. So, you know, those are some of the things that we were thinking about. On the left-hand side, there's two maps. The first one is just Bitcoin. So we joined the Bitcoin network and we started pulsing some data there. It wasn't that exciting. So we said, well, why don't we add another network here? So then we added the Ethereum. So you can see there's Bitcoin and Ethereum. And then our future plan is driven a lot by, you know, the people working on this research. And, you know, we're going to add a couple of more networks, and then we're going to try to compare the risks across the different, you know, popular networks. Right now, we're focused towards the larger networks. You know, at some point, if we have enough resources and, you know, excitement, we'll start moving down. But, you know, we just think of this as a way to engage the community, but also we want to be very rigorous and independent. So, you know, we don't want like Cardano to be funding all the research and then we'll be promoting Cardano. We don't want that. We want to try to be as independent as possible so that we can have a very nice sort of view. One thing that I don't know if people are familiar, at the University of Chicago, there's this thing called CRISP, the Center for Research on Security Pricing. We're trying to parallel that. So there, a lot of graduate students will take some historical data on stocks and bonds and write dissertations. So that's what we're sort of envisioning, a place for graduate students to come and, you know, take the data, do further research and continue to build. You know, so we're trying to keep it as simple as possible so everybody understands what they're visualizing here, and also, you know, use it as a platform for further research. And with that, I will stop and let Veronica kick me off. Thank you, Tony. Thank you. I really enjoyed IAA, and we're 100% supporters of you guys. And I hope that next year we can get some more MBA students actively involved. Thank you.
Thank you so much, Jim. Appreciate it. All right, our final speaker is Frank Fradrick from EdgeCase Research.
Thanks, Tony. Could I do an audio check and make sure you can hear me okay?
You're good.
Excellent. Yeah, thanks to Tony and I for pulling this together. This has been a super dense set of talks, and enjoyed it so far. I'll apologize, I can't be on camera today, I'm traveling. So maybe question to you all is, by the end, try to determine if it's actually Frank or if this is an AI system that's perhaps briefing you. In any case, I'll introduce EdgeCase Research. We're a smaller company. We're about 80 folks now. We're very focused on safety engineering. We do safety engineering services and tools across a number of different industries, largely defense is where I focus, but we're also in the commercial space and doing tool development as well. We're a spin out from Carnegie Mellon. The National Robotics Engineering Center is where our founders were working on robotics for a long time. And we took some of the commercial potential there with things like stress testing, autonomy architectures, and started EdgeCase in 2014. I joined about 4 years ago in 2018 after working with the Army for a number of years doing testing. Today, we've got about 80 folks spread across Pittsburgh, where our main office is, and also in Munich, and then a number of remote folks. And like I mentioned, we've got customers that are really all over the board. My focus is in defense. I'm the vice president of our defense business unit. We've got a commercial focus that looks at robotaxi and autonomous trucking in that industry, actually with a focus on insurance. So if you think about how do we identify risks and then go next step to how do we set prices for those things, that's the challenge that we're investigating there. And then also a group, again, that focuses on tools and enables our other services and focal areas. So I want to talk today, again, about system safety. For folks who aren't aware, there's, system safety has existed for quite a while. And the practices here largely map nicely to a systems engineering V. You think about understanding your system, you think about knowing where is it going to be deployed, how's it going to operate, what missions are we attacking with these systems. And with that kind of a baseline, you can do hazard analysis that is rigorous, methodical, covers the full system. And you end up with these deterministic safety functions that are really able to be analyzed and wrung out to a low level of detail. Specifically in the software realm, when you think about high criticality software, it drives practices that influence the whole development lifecycle. So it's not just that we've tested to show safety, we've got evidence of safety requirements, safety design, safety coding practices, things like path coverage and whatnot that we want to show that we've really fully understand the safety critical software and it's analyzable. So then we compare and contrast that with systems that are more complex, autonomous, and getting into machine learning and broader AI type of enablements. And here in the bottom left, we got an example of some findings that we have, right? So can we really trust these systems yet? They're certainly, as everybody's kind of alluding to here, we're on the path there, but not quite yet in most cases. We have a tooling that does stress testing on autonomy that's specifically for camera-based machine learning systems and trying to detect pedestrians. So our hologram tool found these interesting, false negatives here, where things that you might use to try to attract attention of human drivers, like a vest that's yellow, or maybe some signage that actually fooled a system because that wasn't in the training set. And so as others have said, data and trying to find that right training data is such a challenge here. Other examples, being adjacent to other objects, having differences in height. You think maybe you'd be more careful around a child, right? But in this case, that the height of the child was a distraction to the train system, or something like a walker, right? And maybe some other obscuration in the foreground there. But in any case, yeah, I think we're thinking a lot about what are these challenges and how do we attack it? What are the solutions that are here now, and where do we go next? So the start here, we worked on UL 4600 as a relatively new standard. It first came out in 2020. That's for looking at the evaluation of autonomous products, really from a safety perspective. And the theme of UL 4600 is really around safety cases. So I noticed Don McDermott said that in North America, we're less reliant on safety cases in a lot of different industries, and that's true. We're trying to change that. We think there's a lot of power here, a lot of value. Because of the complexities, right? And especially in some of the newer industries like autonomous, road vehicles, the government regulations, the standards, sometimes even state by state, there's large deltas, right? So putting those arguments together in a structured way and talking about how you're solving those problems is really critical. And for those who are familiar with some of the other standards, like maybe ML Standard 882 or the ISO functional safety standards, the intention with UL 4600 is to work together with those. So we can really use these as puzzle pieces to build our assurance case and have a holistic argument that addresses safety in a full way. And we're also investigating, how can we merge these things together, other abilities? So security, quality, reliability, whatever it may be, there's ways to attack this so that we're maybe getting credit for our evidences in multiple domains for multiple assessors. Next, please, Tony. So looking again at more, where do we go next? Really building blocks, right? So we think about looking at these system safety standards that we know and love, that we have for a long time. We certainly can't throw those away and start. So I appreciated the recent discussion here about looking at the systems engineering perspective, and that we have to fit the AI pieces into these larger systems engineering perspectives. And then building off of those known standards with more progressive, novel standards and ideas like the ones that have been presented throughout this set of talks, which are excellent. I also want to note too, for folks who are really out there doing this in the real world, there's a lot of good safety contract language to help be aware of what might be asked of you if you're trying to insert your AI into real systems. This Joint Software Safety Engineering Handbook has some example contract language to be aware. And so if you're going to insert this and rely on it and say, well, I think this is safe, that has some of the details of what might be asked of you to provide for your AI software. As we're trying to get out to the field, we need to test safely. This is a big thing, right? We see things like safety drivers, we see things like dedicated ranges, but we also see people testing on public roads, sometimes not maybe necessarily marked. So I think that's a concern that hits everybody, every one of us, right? You see, that Tesla go by. Is there somebody in the driver's seat, or what are they doing? So we're always looking at that. But there's definitely some guidance there from from ISO and the DoD space, where we think about what are the right things to do. How do we progress in a step-by-step way? Crawl, walk, run, so we have building blocks that we can trust and leverage procedural safety and range mitigations and whatnot, until we have some trusted safety devices and maybe some degraded or safe modes that our systems have been verified to implement. And getting to those trusted pieces, we look at safeguarding AI through design. Intentionally architecting our systems is critical. If we know we're going to have some more complex pieces to our system that we need to make it perform, if there's ways to do simpler checking via safety systems, that's always going to be a successful method. Lets us do our faster, maybe DevOps type agile practices on our performance systems that are, in this case, acting as a quote unquote doer. If we can satisfactorily check the performance of that doer with a safety verified system, it's hopefully simpler, right? So if we can churn and do our CI/CD and pump out new deployments overnight, but our checker hopefully is verified and can find those thresholds and verify them, it has much less change over time. And then the last piece here is just looking at measurement, because we talk about data to build our system, data to monitor what it's doing as far as safety or security or other abilities. And again, this goes back to the safety case approach. If we have a deliberate way to identify the claims and arguments and the evidences that we need to track, that helps us whittle down our data set and looking at the ways to get that data, not only, as working towards deployment and the systems V cycle, but also post deployment once we're actually out in the world, monitoring for those things that maybe broke some assumptions or maybe even near misses that wouldn't trigger a quote unquote mishap, but things that we can use to bring back and better the system before that next big event occurs. So that's all I have for today. We're out there doing this in the real world with different industries. Excited to talk with folks who want to partner and team. We're always looking for places to pilot and try to show progress in things like assurance cases, things like AI methods that are verifiable, but also while we're ensuring safety along the way. So thanks very much for your time, everyone.
Thank you, Frank. I'll also add, you talked about areas of concern. One of particular concern to me is the initial trend of self-certification. I think that's, at this point in the game, that's extremely dangerous, and we need more involvement from third-party independent outfits like yourself, like yours, to ensure that what's going out, especially on the roadways right now, is reasonably safe. I don't know. After all we've heard today, I think we have a way to go.
Wholeheartedly agree, Tony. Thanks.
All right. Well, I'd like to thank everyone. I want to thank in particular Ken Schmidt. I also want to thank Veronica Cook for their hard work and keeping everything organized so that we were able to get through all of these talks. We have a few extra minutes. I just wanted to, if you can, for those of you who can stick around, I wanted to put in a plug for an announcement that we made yesterday for IAA. We announced our next round of funding, and it's a little bit different than our first round. This time around, what we want to do is encourage collaboration and teamwork, building teams of researchers to go after large external funding opportunities. And so we just made the announcement, the initial announcement yesterday, and are starting to make the rounds. We'll have a document within the next week or so. But the reason that I'm saying to this mixed group is that many of the worthwhile funding opportunities out there require collaborations across universities and with industry partners and so forth. And so I wanted to give you the heads up so that if you're working on something that you feel is where it makes sense to pursue some kind of a team-oriented funding opportunity, please keep us in mind. Reach out to contacts or reach out to me or to Carol LaPointe or Jim Bellingham, and we'd be glad to facilitate connections to people within Johns Hopkins. So our funding, it comes from our president's office, and so it does have restrictions. And so the fund all this funding can be used to enable certain aspects of events like workshops. So we think that that this will be very useful over the next few months to build teams to go after large funding opportunities. Also wanted to just put in a plug for there's the second iteration of the IAA Conference on Assured Autonomy is close to being announced if it's not already. I don't have many details, but I would just encourage everyone to consider publishing or submitting your papers to this conference that IAA is supporting as a sponsor, and we'd really like to see this as one of the focal points for Assured Autonomy. With that, we will give you some time back, and want to thank you once again. Appreciate those of you who contributed, those of you who sat in. Hopefully you're thinking in terms of collaborations, new connections. I wrote down several myself, and so we hope that this is useful. If you find that it is, please let us know, and we'd be glad to schedule more of these in the future to enable new collaborations. So with that, I want to thank you and have a great day. Thank you very much.